Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to present my econometric project, and my lecturer is Dr. Wan Nurahini Azni Zainuddin. My title for this project is The Causal Effect of Life Expectancy at Birth, Alcohol Consumption, Obesity, and Urban-Rural Demographics on Death Rates. My name is Wan Muhammad Yusuf Yohamuddin, and my metric number is 1222581. For the first part, we are going to look at the abstract. In this study, a regression model is used to explore the relationship between death rates, our dependent variable, and various social health factors. The independent variables include life expectancy, alcohol consumption, obesity levels, and the disruption of urban and rural populations. Using a broad dataset, the research employs multiple regression techniques to assess how each factor influences death rates. The results indicate that life expectancy and obesity are the most significant factors, while alcohol consumption and urban-rural disparities show a secondary influence. This finding emphasizes the complex nature of mortality shaped by a combination of health behaviors and demographic factors. Overall, this study provides valuable insight into public health dynamics, offering a foundation for informed policy decisions aimed at improving population health. Chapter 1: Introduction. Understanding the factors that influence death rate is crucial for developing effective public health guidelines and programs. Death rates are influenced by a variety of factors, all contributing to the overall population growth rate. Among these, life expectancy at birth, alcohol consumption, obesity, and the urban-rural population distribution are key global health indicators. Life expectancy at birth serves as a measure of the quality and longevity of life, incorporating factors like healthcare, economics, and the environment. However, non-physical health indicators such as alcohol consumption and obesity are recognized as significant risk factors for chronic disease, which in turn significantly affect mortality rates. Furthermore, the urban-rural divide highlights disparities in access to resources, healthcare facilities, and overall health outcomes. While the interaction of these variables on death rates is known, it is still insufficiently explained, particularly when considering socioeconomic context. For instance, while obesity and alcohol use are well-established health risk factors, there is a relationship with urban versus rural environment, and life expectancy is not fully explored. This research aims to bridge this gap by analyzing how these independent variables impact death rates, offering new insight into how socio-economic factors and health behaviors interact in shaping mortality trends. Now, let's look at the research problem. For the problem statement, high mortality rates are a significant social issue, complicating healthcare systems and influencing policy decisions. While many studies have explored factors contributing to mortality, few have examined how these factors interact, particularly in the context of smallholder farming households. Furthermore, the role of the urban-rural divide in exacerbating these effects is underexplored. This paper aims to bridge this gap by analyzing the relationship between life expectancy, alcohol consumption, obesity, and urban-rural population distribution and on death rates. By revealing this connection, the research seeks to provide practical insight to help policymakers address key drivers of mortality. Chapter 2: Literature Review. The death rate is a critical determinant of public health, shaped by various factors such as communicable and non-communicable disease, socioeconomic status, and healthcare infrastructure. This literature review synthesized key findings on the primary causes of mortality worldwide, specifically focusing on obesity, alcohol consumption, stroke, and preterm birth. Additionally, the disparities in death rates between high-income countries and low and middle-income countries are highlighted, underscoring the need for targeted intervention to address these inequalities. Life expectancy and mortality rates are among the most important indicators of population health. These measures are influenced by a complex mix of healthcare access, socioeconomic factors, public health policies, and lifestyle choices. This review delves into the global trends in life expectancy and mortality rates, particularly the implication for non-communicable disease, communicable disease, and mental health issues. Recent statistics show a steady increase in global life expectancy, which brings important implications for mortality rates, especially regarding age-related disease. As life expectancy increases, we see a rise in cancer rates and other chronic conditions like atrial fibrillation. In fact, cancer cases are expected to surge, especially in transitioning countries, leading to higher mortality rates. However, cancer mortality rates are not declining uniformly across the globe. while high-income countries have seen a decrease in cancer mortality due to improved healthcare and lifestyle changes. Many uh, Many are experiencing rising cancer mortality. This is driven by a combination of lifestyle changes and increased life expectancy, which are not always matched by improvements in healthcare. Alcohol consumption is another significant risk factor for mortality and chronic disease, yet its relationship with health is complex and multifunctional. The the effect of alcohol on health depend on consumption patterns, genetics, and existing health conditions. The literature reviews focus on recent findings that explore the link between alcohol consumption and chronic disease, highlighting alcohol as a modifiable risk factor. There are notable gaps in our understanding of how alcohol consumption directly affects mortality, and this review identified key areas for future research. Excessive alcohol intake is particularly concerning due to its indirect link to chronic liver, such as alcoholic liver disease, which can lead to conditions like cirrhosis and hepatocellular carcinoma. For individuals with advanced cirrhosis, life expectancy can drop dramatically, with a median survival of only 1 to 2 years. The increased incidence of HCC, often a consequence of chronic liver disease, highlight the severe health risks associated with excessive alcohol consumption. Addressing alcohol consumption in public health interventions could have a significant impact on reducing liver disease and cancer incidence, and ultimately mortality rates. Obesity is another major contributor to mortality, especially when combined with other chronic disease. Studies such as one by Garvey et al. Have shown that weight loss intervention can improve cardiometabolic health and reduce the risk associated with obesity. Moreover, obesity's impact extends beyond chronic disease. It plays a key role in the severity of infectious disease, particularly during health crises like COVID-19 pandemic. Research by Popkin found that obesity increased the risk of death in COVID-19 patients by 48%, underscoring the role of obesity in exacerbating health risk during infectious disease outbreaks. Additionally, obesity contributes significantly to diabetes risk, which is associated with higher mortality in infectious disease like COVID-19. Chronic inflammation, a hallmark of obesity, plays a key role in the development of insulin resistant and type 2 diabetes. This condition in turn lead to a host of complications that further increase mortality risk. Research by Zattirel and Desi and Zewatir suggests that addressing the inflammatory pathways associated with obesity could help reduce the mortality risk linked to this condition. Implementing therapeutic strategies aimed at reducing obesity-related inflammation should be a priority in public health initiatives to mitigate the mortality burden associated with obesity. In conclusion, this review highlights the complex interplay of factors contributing to mortality, with a focus on obesity, alcohol consumption, non-communicable disease, while life expectancy continue to rise globally. This brings both opportunities and challenges, particularly in managing chronic disease and their impact on mortality, by addressing key risk factors like obesity and alcohol consumption, and focusing on disparities between high income and low to middle income countries. Public health intervention can be more effective in reducing global death rates and improving overall health outcomes. Chapter 3: Data Description and Methodology. Okay, data description. We are using 55 data for this observation. The dependent variable as the main outcome variable be analyzed, and independent variable we have five independent variable, and include both continuous and binary variables. Each independent variable represents a potential factor influencing y. The binary variable is the vector converted into the binary, which is 0 and 1, and the black one is the equation for our multiple linear regression. And our methodology is data collection, model specification, hypothesis testing, confidence intervals, model performance metrics, multicollinearity assessment, residual variance analysis, variable dropping, interpretation of our results, and goodness of fit comparison. Next is limitation. The regression analysis used in this study has several methodological limitations. First, the dataset from the World Bank and WHO may not be fully reliable potentially missing data from certain countries or regions. The reliance on self-reported data like alcohol consumption and obesity prevalence introduces the possibility of reporting bias. The linear regression model assumes linear relationship between variables, ignoring potential non-linear interactions. Multicollinearity among variables such as urban and rural populations could also affect coefficient estimates. Furthermore, the analysis is based on cross-sectional data, making it impossible to infer causality or long-term trends. External factors like economic crisis or political instability were not included, which could lead to omitted variable bias. Therefore, cautious interpretation of this finding is essential. Chapter 4: The Results. 4.1, which is descriptive analysis. In this analysis, the death rate data reveals some important insight. The distribution of death rates is slightly skewed, with a mean of 8.37 deaths per thousand people and a median of 8.28, showing that the mean is marginally higher than the median. The mode, which is 9.9, indicates that most frequently occurring value, which is also slightly higher than the both of mean and median. The variation in the data is moderate, as affected by a standard deviation of 1.71, suggesting that most of the death rate values are concentrated close to the mean. However, the death rate range is relatively wide, spanning from 6.02 to 12.8. The sample variance of 2.93 further emphasizes this variability. The skewness value of 0.60 indicates a slight positive skew, meaning a small number of areas or countries exhibit unusually high death rates. Additionally, the kurtosis value of negative 0.018 suggests the distribution is slightly platycrutic, meaning it has fewer extreme values compared to a normal distribution. Overall, death rates are moderately distributed with a slight positive skew. Turning to life expectancy, we see a mean of 71.22 years for a group of 55 individuals. The median life expectancy is 72.73 years, with a standard deviation of 8.22 years, showing a wide spread of life expectancy values within the group. The range is 26.83 years from a minimum of 56.02 years to a maximum of 82.84 years. At a 95% confidence level, we can say there is a 95% chance that the true mean life expectancy lies within a range of 2.22 years from the calculated mean. In summary, both the death rate and life expectancy data exhibit moderate variability, with death rate showing a slight positive skew and life expectancy showing a wider spread with significant variability. Data presented here consists of 55 observations of alcohol consumption. The mean alcohol consumption is 5.66 units, while the median is 5.06 units, suggesting a slight positive skew in the data. There is a considerable spread in the consumption values with a standard deviation of 3.28 units. The mode, which is 11.92 units, indicates an outlier or a peak in the distribution, meaning some individuals have much higher alcohol consumption. The range of consumption is 10.86 units, with a minimum of 1.06 units and a maximum of 11.92 units, indicating significant variation in alcohol consumption within the sample. The high level of confidence in the estimate of the mean is shown by 99.7% confidence level at a 95% confidence interval. Moving on to the obesity data, the mean value is 17.92 with a standard deviation of 7.02, showing a somewhat dispersed distribution. Interestingly, the median is slightly lower than the mean at 18.99, which points to a positive skew in the data. The range of obesity values is 24.43 with a minimum of 5.01 and a maximum of 29.44. The negative kurtosis value of negative zero point 0.1 or zero 0.7 indicates a platycrutic distribution, meaning data is flatter than a normal distribution. The skewness value of the of negative 0.34 suggests a slight negative skew, with more data points appearing on the lower end of the distribution. At a 95% confidence level, we are confident that the true mean obesity level falls within a range of plus minus 1.898 from the sample mean. In summary, the alcohol consumption data shows significant variability with a positive skew, while the obesity data shows a slightly negative skew and a flatter distribution than normal. For last one dataset of urban areas contain 55 observations with a mean value of 51.49, a median of 50.71, and a mode of 94.41. The spread of data points around the mean is indicated by a standard deviation of 23.78. The skewness value of 0.35 suggests a slightly positive skew. indicating a small concentration of high values. The data range spans from 13.02 to 34.41 with an interval of 91.39. This range reflects a 95% confidence level that the true population mean lies within 6.43 units from the sample mean. These statistics help to understand the central tendency, dispersion, and shape of the data distribution in urban areas. Similarly, the rural area datasets, also consisting of 55 observations, has a mean value of 48.51. The median is 49.287, with the mode being 86.981. The standard deviation is 23.78, indicating a similar spread to the urban data. The range between the maximum and minimum values is 81.395. The 95% confidence level provides a range around the sample mean, helping estimate where the true population mean likely falls. 4.2 is sample correlation. Urban population tend to have higher life expectancy but also slightly higher death rates due to factors like pollution and stress. Rural population, while having lower death rates, face challenges in healthcare access, leading to lower life expectancy. Lifestyle factors like alcohol consumption and obesity both negatively affect life expectancy, contributing to chronic health conditions that reduce lifespan. Urbanization, tough linked to better health outcomes, is associated with higher death rates, while rural areas are grappling with rising alcohol consumption and obesity, which could negatively affect health outcomes. To improve health outcomes, targeted public health interventions should focus on reducing alcohol consumption and obesity, then addressing healthcare disparities, particularly in rural areas. By doing so, we could significantly enhance population health and reduce the health gaps between urban and rural regions. Okay, 4.3 is variation inflation factors, which is VIFs. For death rate and life expectancy is 1.032681,879, and death rate and alcohol consumption, the VIF is 1.005751,407. For the death rate and obesity is 1.0167,407. For death rate and urban population is 1.010609, and for death rate and rural population 1.010609. The model is not experiencing problems of multicollinearity. All dependent variables are sufficiently distinct because the highest VIF value is 1.0106, far from the threshold that presents constants. It's also the lowest possible value. Thus, the regression coefficients are reliable while the results of the model are stable and robust. For the multiple linear regression model, we get that the R squared is 0.2361, which conclude that 23.61% for the R squared, and the coefficient for S1, which is the life expectancy, is negative 0.122. The coefficient for the alcohol consumption is negative 0.0257. The coefficient for the obesity is negative 0.0373, and the coefficient for the binary is 1.849, and the number sample is 55. 4.5 is variance of the slope coefficient. From the formula, we get that the life expectancy variance of the slope, we get the 2.886599369 for the beta 2, which is alcohol consumption above 15 years, 2.96 uh, 3892309 for beta 3, obesity above 18 and adult, 2.931858, and for the urban population we get 2949645, and it's the same for the rural population. For the residual variance, we get from the formula, which is the residual sum of squares divided by degrees of freedom, which is 120.6739284 divided by 50. Then we get the answer is 2.4134785668. 4.6. Explain how the residual variance impacts the estimate variance of the slope coefficients. The residual variance denoted as 2.4135 plays a key role in the variability of the estimated variance of the slope coefficient in our multiple linear regression model. This variance represents the spread of the dependent variable around the regression line and is related to the values of the predictors. The larger the residual variance, the higher the uncertainty in the slope coefficients, making it harder to achieve statistical significance. In this model, the residual variance affects all coefficients, including binary variables, in a consistent way, contributing to imprecision. The practical implication is that by reducing residual variance through a better fitting model, such as adding relevant predictors or improving data quality, we can achieve more reliable coefficient estimates, which would lead to clearer interpretation of the model. 4.7 is not against one-sided and two-sided alternative hypothesis for all the variables. For x1, which is life expectancy, the coefficient is negative 0.122. The null hypothesis is beta not equal to 0, and the alternative hypothesis for one-sided is lower than 0, and the alternative is not equal to 0. And for the alternative hypothesis two-sided and the null hypothesis, for all the variables are the same, which is equal to 0 and not equal to 0. For the variable 2, which is the alcohol consumption, alternative hypothesis for one side is below than 0. For the x3, which is the obesity, is below than 0. For the s4, which is the urban area, we have urban population higher than 0. And the same with the rural population, which is higher than 0. 4.7 also discuss whether all the independent variables are statistically significant at all levels. The analysis supports the hypothesis that we have control over the p-value for each variable at different significance level. Variable x1, x4, and x5 are statistically significant at the 0.01, 0.05, and 0.10 levels, indicating that influence the dependent variable and their coefficients are expected to be non-zero. Conversely, x2 and x3 have p-values greater than zero point 0.1, which is suggesting they are not significant in the current model. The larger coefficient for S1 and S5 show they explain more variance in Y, while X2 and X3 contribute minimally, indicating they could either be omitted or warrant further study. 4.8 is the 95% confidence interval for slope coefficient. The table shows all the 95% confidence interval for slope for every variable. And the discussion, we can say that the 0.95 confidence interval for its slope coefficient clearly highlight the significance of the certain variables. For x1, s4, and s5, the confidence intervals are above 0, confirming their statistical significance at the 0.05 level. This aligns with the result from hypothesis testing, where these variables were deemed significant when the p-value was less than 0.05. In the contrast, the confidence intervals for x2 and x3 include 0, supporting the conclusion that these variables are not statistically significant at the 5% level. Overall, the findings from the confidence interval and this reinforce the result of hypothesis testing, making it easier to trust the conclusions regarding the significance of the independent variables. As such, x1, x4, and s5 should be prioritized in the analysis of the dependent variable, while x2 and s3 can be excluded as they appear to have no meaningful impact in the current model. 4.9 calculate the interpret the adjust R squared value for the model. Using this formula, we get the adjusted R square for the new one is 0.175086772. How does it differ from R square value for the model, and what does it tell us about the goodness of fit? The R-squared value for the model is 0.2362, meaning 23.62% of the variation in the independent variable is explained by in the independent variables. However, the adjusted R-squared is slightly lower at 0.1751. This adjustment accounts for the number of predictors in relation to the sample size, recognizing that some predictors like x2 and x3 may not contribute much to the model's variability. The modified R2 penalized such predictors, offering a more reliable measure of model fit. Despite the lower adjusted R squared, it suggests a moderate fit, showing that while the model explains some variation, there is room for improvement. This highlights the importance of refining the model by either removing less impactful predictors or incorporating additional relevant variables to enhance its predictive power. 4.10 drop one of the independent variables and run another multiple linear regression. These are the result for the new multiple regression when we drop the binary independent variable. We get the R squared equal to 0.074 and the adjusted R square is 0.0190. Now, let's discuss the impact of dropping the binary variable from the regression model and its implication for omitted variables bias. After removing the binary variable, we observe changes in the magnitude of the remaining slope coefficients, though the sign remain consistent. This suggests the relationship between the predictors and the dependent variable are stable, but their strength has shifted. The binary variable likely captured unique effects that are now redistributed among the other predictors. This redistribution highlights a classic case of omitted variable bias, where leaving out a relevant variable that is correlated with both the dependent variable and other predictors can distort the coefficient magnitudes. As a result, the model may lose explanatory power, making the coefficient less reliable for interpretation. This emphasizes the importance of including all relevant variables to avoid bias and ensure accuracy in regression analysis. In this case, while the signs remain stable, the magnitude shifts remind us of the critical role that omitted variable play in influencing regression results. Thank you for lending your ears. That's all for me. Thank you.